Welcome to the debate. Today we're looking at, what happens when you try to pack a massive 7 billion parameter language model into a space so strictly bounded by physics that you just, you can't throw hardware at it.
Right. You literally cannot buy your way out of this one with bigger servers.
Exactly. So we are dissecting the architecture of the Monster Mesh distributed inference system. This is the engine hidden deep within the fork-join monorepo, and its explicit purpose is to run the quencoder 7B model across severely resource-constrained edge networks.
Which is a nightmare of an environment to work in.
Oh, completely. And to do this, the engineers didn't just write clever code. They applied an advanced, highly abstract mathematical framework based on topological quantum field theory, or TQFT.
And we should clarify right up front, our entire analysis today is strictly grounded in their architectural documentation. We are digging directly into their implementation files, the layer stations, the copper-dism shards, and this overarching, somewhat intimidating topological philosophy they call the manifold ticket frame.
The core tension here is whether applying high-level abstract topology to a physical computing problem is a brilliant necessity or, a dangerous distraction. I take the position that when you are operating in an environment with hard physical walls, this strict mathematical alignment is the only way to make distributed large-scale inference possible.
The only way?
Yes, the only way. I mean, the framework is an engineering triumph because it bends extreme constraints into operational efficiency.
And I take the completely opposite view. Theoretical purity is intellectually fascinating, sure, but in this system it acts as a really dangerous illusion. It actively obscures systemic brittleness.
I wouldn't call it an illusion.
Well, when you look closely at their own logs, what you find is an over-engineered framework that basically forces standard engineering errors to manifest as catastrophic, silent failures instead of, loud, easily fixable crashes.
Let's start with the physical reality of the constraint, because if you don't understand the constraint, the math just looks like overkill. If you're a standard back-end engineer listening to this, you're probably used to spinning up a container with gigabytes of RAM.
Or tens of gigabytes, yeah.
Right, but the Monster Mesh relies on edge workers that are hard-capped at a 128 megabyte request budget.
Which is nothing.
It is nothing. If a process hits 129 megabytes, the runtime simply kills it. Now look at the quencoder 7B model. Just the token embedding weight alone, like the very first layer that turns text into numbers, is roughly 306 megabytes.
So it fundamentally doesn't fit.
Exactly. You physically cannot fit a 306 megabyte tensor into a 128 megabyte worker. It defies the laws of physics of that specific environment. So they implemented the fluid memory invariant. They sliced the model's vocabulary across 8 disjoint pieces, which they call copper-dism shards.
Right.
And by doing this, the memory footprint for any single shard drops to about 38 megabytes, which is, comfortably under the limit.
Sure, but slicing data into chunks is standard distributed systems design. We've been doing that for decades. The actual point of contention is how they stitch it back together.
Well, yes, but it's how they do it that elevates this from a standard chunking exercise to something profound. They use the Atiyah-Siegel TQFT functor. Think of this functor as a set of incredibly strict geometric rules for stitching independent spaces together.
Highly theoretical rules.
Highly theoretical, but practically applied? Imagine a symphony where every musician is locked in a separate soundproof room across the globe. You can't have a conductor waving a baton to keep them in time because the latency would ruin the song.
So they use math instead of a conductor?
Precisely. The sheet music itself is mathematically constructed to guarantee they stay perfectly on beat when you compile the audio. This math guarantees that if you have piece A and piece B, their boundaries will perfectly neutralize each other without overlapping. They aren't writing traditional mutex locks or complex database joins.
No, they're just hoping that topology holds.
They aren't hoping, they're proving it. The theoretical principle of topology directly translates into a lock-free, physically efficient operation.
The problem is that the symphony you're describing assumes every musician actually plays their instrument perfectly every single time. And in edge computing, musicians drop their instruments, their strings break, or, their soundproof rooms just lose power entirely.
Well, edge networks are volatile, yes.
Right. And when you read the known trap section of their architecture logs, the illusion of mathematical perfection just shatters. Because the abstraction layer is so incredibly dense, when something goes wrong, the system doesn't just halt and throw an error. It assimilates the error and produces complex, silent hallucinations.
You're referring to the not file bug, aren't you?
I am absolutely referring to the not file bug, the catastrophic off by one bug in their not file format. Let's walk through what actually happened there. The system relied on an encoder that pre-padded JSON metadata.
Okay, standard practice.
Sure. Let's say the metadata was 120 bytes, but it was padded out to 128 bytes with trailing spaces. However, the reader side expected the unpadded length to dictate exactly where the binary payload started. Because of that discrepancy, the payload offset was shifted.
By a single byte.
Right, a parsing mismatch.
But look at the consequence. Now, in a normal, pragmatically engineered system, trying to read a binary tensor from the wrong offset throws an out-of-bounds error or a header validation fails. The process crashes loudly, you get a stack trace, you fix the bug.
Yes, but every single quantized block read into the previous block's memory region. It was reading the F16 superscale value from the wrong bytes entirely.
And it propagated?
It just perfectly mathematically propagated garbage, silently producing logic outputs laced with not a number values. The topology didn't catch it at all.
But wait, let me jump in there, because you're pointing to a serialization bug that was ultimately identified and patched. The encoder and reader were brought into alignment. You really can't indict the entire topological framework based on a metadata padding error.
I absolutely can, because the framework's design philosophy is what made the bug so dangerous in the first place. The topology was blind to the data corruption because the shape of the execution remained valid.
Let's look at the actual mechanics of the TQFT codeboard as a merge, because that is where the resilience of the system actually proves itself. You mentioned edge workers dropping their instruments earlier.
Yeah, network timeouts, throttles.
Right. The math dictates that the embedding lookup is multiplied across disjoint partials. The 152,000 plus tokens in the vocabulary are spread across those 8 shards we talked about, meeting end-to-end with no gaps. When a request comes in, the shards that do not own the specific token in question emit an all-zero vector. Because of the Frobenius identity in their topology, you can sum these 8 disjoint float32 arrays and produce the exact correct embedding row. It's a lock-free operation mathematically guaranteed to avoid double counting.
Mathematically guaranteed on a whiteboard, yes. But let's talk about the actual implementation. How did they coordinate those 8 shards?
Originally, the coordinator logic used a standard promise.all in JavaScript.
Which requires all promises to resolve.
Exactly. It requires all 8 network requests to resolve successfully. And we're talking about edge networks. They jitter. Multi-tenant CPU throttling happens constantly. Cold starts delay execution.
That's the nature of the edge.
Right. And because they used promise.all, if just one of those 8 shards timed out, which is a completely routine occurrence in this environment, the entire prefill step failed. Your beautifully elegant, lock-free math brought the whole inference engine down because it couldn't handle basic network reality. That is precisely why the engineering team upgraded the coordinator to use promise.all settled. And this, honestly, is where the framework shows its maturity through graceful degradation.
Graceful degradation is doing a lot of heavy lifting there.
Hear me out. Think of it like a multi-lens telescope observing a distant galaxy. If one lens cracks or gets temporarily obscured by a passing cloud, you don't scrap the entire observatory and shut down the mission.
You just get a bad image?
You accept a localized blur in the image. With promise.all settled, if shard 4 times out, the system doesn't crash. You still get perfect embeddings for every token not in shard 4's range. The tokens that were supposed to come from the missing shard simply emit as all zeros.
Which is a huge problem.
But the model continues computing with localized inaccuracies rather than a fatal application-killing crash. For a user on an edge device, getting an answer that is slightly degraded is far better than getting a 500 internal server error.
Hold on, I'm sorry, but that is a massive mischaracterization of how language models actually work. Feeding an all-zero embedding row into a transformer is not graceful degradation. It is silent corruption.
It maintains the topological invariant.
Who cares about the invariant if the output is garbage? Think about the attention mechanism. The model relies on rich, highly dimensional semantic vectors to determine relationships between words. If you feed the attention head a zero-filled array, the math continues like the matrix multiplication doesn't crash, but the semantic meaning of that token is entirely obliterated.
But only for that token.
It poisons the well. The downstream layer stations just happily fold those zero rows through the feed-forward networks, and eventually the model emits near-uniform softmax probabilities. To the end user, this doesn't look like a localized blur. The system returns repetitive, decoded gibberish.
It's an edge case fallback.
As an engineer maintaining this platform, I would much rather have a loud, hard crash that pages me in the middle of the night than a system that silently hallucinates garbage and pretends everything is fine just because the topology held together.
You are ignoring the unforgiving nature of the environment, though. A hard crash on an edge worker doesn't page you so you can fix it in real time. It just drops the user's request entirely. They are literally fighting for survival within a 128 megabyte sandbox.
I'm not ignoring the sandbox. I'm saying the sandbox rules are creating unmanageable complexity.
This brings us right back to the fluid memory invariant, which dictates the entire forward pass of the model. They enforce a draconian rule. No layer station worker is ever allowed to hold more than the bytes required for a single phase of a single layer at any given time. We're talking about 56 separate load and evict cycles per station per forward pass.
Which is an absurd amount of I/O overhead.
But it's necessary. Look at the feed-forward network, the FFN. The gate projection and up projection tensors are roughly 50 megabytes each at their quantized state. If an engineer tried to write a traditional combined forward call, the worker would need to hold 100 megabytes just for those two tensors.
Plus the activation memory.
Exactly. Plus the activation memory, plus the runtime overhead, they would blow past the 128 megabyte ceiling instantly. So by topologically separating them, the system evicts a gate projection from memory before loading the up projection. This ensures the worker peaks at roughly 63 megabytes mid-forward. I mean, it is an intricate, perfectly choreographed ballet of memory management.
It is choreographed, sure, but look at the sprawling complexity required to keep that ballet from turning into a pileup. To maintain this memory invariant, they had to build massive asymmetrical infrastructure.
Infrastructure that works.
Barely. Let's look at the dual dequantization paths. Because those cobornism workers have to fetch one row at a time to stay under the memory limit, they had to write a custom JavaScript dequantizer. Why? Because you can't load a 306 megabyte tensor into WebAssembly linear memory without crashing the worker.
Right. WASM memory is contiguous, so it would break the budget.
Yes. But then for the deeper layered tensors, which are loaded entirely into linear memory, they use a compiled Rust dequantizer. They are maintaining two completely separate implementations of IEEE 754 subnormal floating point handling just to keep this invariant alive.
It's a pragmatic optimization.
And look at the caching hierarchy required to make this performant. They use durable objects to cache the weights, storing 128,000 raw quantized rows versus only 18,000 dequantized rows. This wild asymmetry directly caused the key value cache poisoning bug.
Ah, you mean the hard-coded row size issue.
Yes, exactly. An earlier version of their code hard-coded the float 32 row size for 2.4 quantized models. As a result, the durable object wrote rows of the incorrect byte length into the KV cache.
Which was an oversight.
A massive oversight. Because the system was so heavily optimized to meet tight latency budgets, they prioritized read speed over runtime validation. Those poisoned cache entries persisted for their full 24-hour time to live. For an entire day, the system was silently ingesting structurally compromised arrays. And again, the math just kept right on crunching.
But what is the viable alternative here?
The alternative is writing a system that validates its own memory bounds before computing.
The alternative is that the model doesn't run at all. You have to acknowledge the reality of the hardware constraint. If they didn't implement this highly complex durable object LRU caching strategy, every single token request would require fetching weights from R2 cold storage.
True, the latency would be terrible.
It would be measured in minutes, not milliseconds. The inference engine would be completely non-viable. Yes, the dual dequantization paths add engineering overhead, but they are a pragmatic bridge. The JavaScript path streams the embedding slice because WASM linear memory constraints demand it. The Rust path handles the intensive hot loops for the deeper layers. They aren't adding complexity for fun, they are pushing the absolute boundaries of what distributed edge networks are capable of executing.
Pushing the hardware boundaries is one thing, but pushing your engineering team into a philosophical straitjacket is another. And that perfectly transitions into the overarching architectural framework governing all of this, the Monster Mesh.
A manifold sharded frame. I actually find this to be the most intellectually ambitious part of the entire fork-join project.
Ambitious? Maybe. Usable? No.
They aren't just treating code as text instructions executed sequentially. They are treating execution logic as a topological shape, a persistent barcode, essentially. They built this internal tool, the holographic handshake visualizer, which literally takes 1D execution paths and snaps them into a 3D holographic state.
Right.
And they route this through what they call the sovereign sieve. The sieve operates on a simple mantra. If it folds, it fits. It acts as a media-agnostic container that guarantees structural recurrence. If a function returns a state that doesn't logically align with the topology, the sieve simply discards it.
If it folds, it fits. I mean, it sounds like a catchy slogan, but consider what happens to the code that doesn't fold. When you examine their 5 deaths integration contract, the reality of working within the Monster Mesh becomes incredibly restrictive.
It establishes boundaries.
It establishes a dictatorship. They mandate that standalone modules, things like the mat-vec memo or the amplituhedron cache, must be developed in total isolation. And then they enforce a draconian single-author rule for foreground integration.
Well, to maintain consistency.
Only the designated foreground session is allowed to edit the mastermodel.rs and wasmbindings.rs files. Furthermore, the documentation explicitly states that the manifold chromoerotic frame rejects anything exhibiting non-triton symmetries or pure chaos,
which are unmappable states.
But if a piece of execution data doesn't have the proper topological holes for the sovereign sieve to latch onto, the manifold collapses. They literally vent the data out of the system and classify it as bizarro noise. When your architectural framework forces you to look at real-world, unpredictable execution data and dismiss it as bizarro noise just because it doesn't fit your pristine mathematical model, I mean, your abstraction has stopped being a useful tool. It has become a religion.
That is a very strong accusation. But the strictness is the entire point. The 5 deaths contract exists precisely so that different subagents and engineers can work in parallel without their code bleeding into one another and causing untraceable regressions.
Untraceable regressions happen anyway.
But the standalone module discipline ensures isolation. And the single author rule isn't some ego-driven power trip. It is a mechanical necessity to ensure that the complex geometric state of the entire pipeline remains perfectly unified during compilation.
It severely bottlenecks development.
It prevents chaos. When the documentation states that pure chaos cannot be expressed, they are simply defining the bounds of their invariant law. You cannot map a persistent barcode onto data that has zero structural recurrence. By intentionally filtering out what they call bizarro noise, they ensure that the execution manifold remains clean and entirely deterministic.
Clean and deterministic?
Yes! They are trying to create a perfectly verified, resilient logic trace across an inherently chaotic edge network. That requires strict boundaries.
But clean and entirely deterministic is exactly the illusion I am talking about. Let's circle right back to that not file bug. The metadata length was pre-padded with spaces, so the offset calculation pushed the alignment exactly 1 byte past the actual payload start.
We established that was a parsing bug.
Yes, but watch what the clean and deterministic system did with it. When the Rust dequantizer initiated its hot loop to read a Q4K block,
It read the F16 superscale value from the previous block's quantized region. It fundamentally misaligned the mathematical reality of the neural network weights.
I know.
Did the sovereign sieve catch that? Did the manifold Fortic frame recognize that the 3D execution state had become fundamentally corrupted? Absolutely not, because the shape of the execution was still valid.
The container held.
Yes, the system asked for a float, and it received the float. The system happily folded the noise. It fed those garbage scaling factors into the hot loop, processed 56 load and evict cycles with perfectly choreographed memory management, and confidently output absolute nonsense to the user.
But that is a surface-level data validation issue, and it was patched. They align the encoder and reader on a single canonical layout that strictly writes the unpadded length. You are pointing at a single pothole and claiming the entire highway system is a failure.
It's a fundamental structural blind spot.
The underlying architecture, the ability to range fetch one row at a time, to dynamically reduce the memory footprint by almost 90% using the TQF for Corbism merge, that foundational math is what allowed this massive language model to run on a 128 megabyte node in the first place.
I don't deny that it runs. I deny that it runs safely.
If we step back and look at the broader picture, I think my position holds strong. When you're faced with the uncompromising physical walls of edge computing budgets, like no persistent local disk, severe latency bounds, and a hard 128 megabyte RAM cap, traditional software engineering fails. Adopting extreme, geometrically inspired invariance is a radical paradigm shift, but it is necessary. The fork-joint monorepo proves that if you rigorously enforce the fluid memory invariant and trust the underlying topology, you can perform computational miracles on minimal hardware.
And stepping back to view my position, the topology is undeniably fascinating, but building a system that relies entirely on perfect geometric alignment inevitably creates a breeding ground for silent, cascading failures.
It's a trade-off.
A steep one. When an architecture is this rigidly abstracted, routine engineering errors, a single byte offset, a hard-coded row size, a network timeout, don't just break the system, they are assimilated by it. They become incredibly difficult to debug because the math ensures the pipeline completes its run even when the underlying data is entirely poisoned. We are moving towards systems so mathematically insulated, the human engineers can no longer rely on traditional logs or crashes to understand what went wrong.
I think where we absolutely find convergence, however, is on the sheer magnitude of the constraints. Both of us have to agree that limiting an AI inference node to 128 megabytes forces boundary-pushing engineering.
Oh, absolutely. Without a doubt.
Whether you view it as a triumph of theoretical physics applied to code or a trap of over-engineering, the methods inside the fork-join monorepo represent a genuinely unique approach to system design.
Unquestionably. The tension between theoretical purity and operational pragmatism here is immense. There is no easy answer, and you can see in the architecture logs that the team is constantly battling at that exact intersection, just trying to balance mathematical ideals with the messy reality of network jitter.
And that tension isn't going to be resolved today. For those listening who want to explore how geometry and execution logic intersect at this level, I highly suggest delving deeper into the source material, particularly the amplituhedron.md documents.
It's a fascinating read, even if you disagree with the premise.
Exactly. Because as edge computing continues to evolve, the question isn't just how small we can compress these models. The question is whether our architectural frameworks will illuminate our errors or mathematically obscure them.